All right, the last topic of the Unit 2 is going to be Lagrange multipliers. This is a multiplier that's going to help us solve some optimizational problems, some max-min problems, that sort of thing. We're just going to touch upon it now, but so we're going to let two functions, f and g, have two variables each, and they're going to have continuous partial derivatives at every point of some set containing the smooth curve g of x of y equals 0. So that'll be our constraint. So if we restrict f to no points on the curve g of x y equals 0, it's going to have some sort of local extrema at x naught y naught, and we have to note that the gradients of that g cannot be 0. Then we have some number, and the symbol usually used for it is lambda. It's called Lagrange multiplier, and we note that the gradient of our f equals that lambda times the gradient of g. All right, so what do we do with this? How do we use this information? So the book has given you a step-by-step way of using the Lagrange multipliers. First of all, number one, we're going to determine the objective function f of x and the constraint function g of x. And does the optimization problem involve maximizing or minimizing the objective function? So the only problems I'm going to be giving you are ones that have an f and a g and are going to be doing just that. Number two, set up a system of equations and use the following as examples. So we're going to find the gradients of f for x, y, so we're going to need to find the partial derivatives for each of these. Similarly, we're going to have to do the partial derivatives for the g function, and then set these two things equal along with a lambda included attached to the g gradient side. And we have to note that we're setting this g of x naught y naught equal to 0, which is what we had to do from our theorem. We're going to then solve for x naught and y naught, and once we find those values, we're going to plug them into our original f equation, the f function, not the g function, and whichever value, whichever xy coordinate minimizes it will be the minimum, whichever maximizes it will be the maximum. All right, so the problem from the homework questions for the following exercise: use the method of Lagrange multipliers to find the maximum and minimum values of the function subject to the given constraints. So we have our f function is x squared and y multiplied by y, and our g function, given the constraints, gxy will equal x squared plus 2y squared minus 6, and that's going to equal 0. We have to set that equal to 0. All right, so let's go about solving for the partial derivatives. So first of all, partial derivative of f with relation to x, well, we have x squared y, so that's just going to be 2xy. Partial derivative with respect to y, take the derivative of y is just 1. We're left with the value x squared, which we treat as a constant here. And this means our gradient of f is 2xyi plus x squared j, given the components and how we solve for gradient. Similarly, let's see, derivative of g with x is just going to be 2x. The only part with x is this first part there. And similarly, gy will be, looks like 4y. And this means our gradient for g is equal to 2xi plus 4yj. All right, so we have that information. So we can look at the x components of these. So once we have these, we know that, say, 2x naught y naught is going to equal some lambda times 2x naught. Well, the 2x naughts cancel, and there we have y naught is equal to lambda. We do the y values, we're given x naught squared is our j component of the f's, and that has to equal some Lagrange multiplier of 4y naught. Well, we know from over here that our y naught is going to equal lambda. So that means that our x naught squared is going to equal 4 times lambda squared. All right. So we have a bit more to do here. Let's see what we can keep there. Okay, so at this point, we've got our g function, so we can use our g function. So our g function above here is x squared plus 2y squared minus 6 equals 0. So using that and using the information we can substitute in, so our y is going to be lambda, and our x squared is going to be 4 lambda squared. So this is 4 lambda squared plus 2 times lambda squared minus 6. So that gives us 6 lambda squared equals 6, which means that lambda equals plus or minus 1. We get lambda squared is 1, which means lambda is plus or minus 1. And if lambda is plus or minus 1, we've got our x squared, x naught squared, is equal to 4 lambda squared. So that's, well, either 1 or negative 1 squared is just 1, so that's going to be 4, which means our x naught is plus or minus 2. So let's take a look at, we're going to plug this into f now. And our f function above, I believe, is just x squared y. It is. So we have f of we have this. So the different possible points. Well, it's x squared y, so whether we use 2 or negative 2, it doesn't matter. So if we take f at plus or minus 2, and then we have a negative 1, that's going to give us 4, what's going to give us negative 4. And if we take a positive 1, that's going to give us 4. That means that this is the minimum, and 4 is the maximum. And we've solved this optimizational problem.